Good morning, everybody. In this talk, I will be discussing about canonical divergence, joint work with Nihat as Lorentz told before. And this new canonical divergence, the aim of this work is to ground the definition of this canonical divergence to the intrinsic geometry of a statistical manifold. So let us first introduce the main object of study in information geometry, that is a statistical manifold, and it is given in terms of a smooth manifold, a Riemannian metric G, and a couple of torsion-free affine connections, nabla and nabla star, that are dual with respect to the metric G. Just to remark that the concept of a statistical manifold is a generalization of a Riemannian metric. Indeed, we can recover the Riemannian geometry by averaging the two dual connections, nabla and nabla star, and getting the Levi-Civita connection. The problem that we aim to deal with in this work is called the inverse problem within information geometry, and it concerns the search for a divergence function that recovers a given dualistic structure. So let us start with the dualistic structure G nabla and nabla star on a smooth manifold M. We aim to define a divergence function in a way that we can recover this dualistic structure. A divergence function is basically a distance-like function defined on the Cartesian product of the manifold M that has to be non-negative and 0 only on the diagonal of this Cartesian product. The dualistic structure is recovered in terms of the second derivatives as far as the Riemannian metric is concerned, and the dual connections are recovered by the third derivatives. All these derivatives then have to be evaluated at the diagonal of the Cartesian product. The inverse problem in information geometry was solved in 1993 by Matsumoto. It showed that given a torsion-free dualistic structure, there always exists a divergence function which induces that structure. However, this function is not unique. Indeed, as we saw before, I mean, all these divergence functions have to coincide up to third order of derivatives. So we can have infinitely many divergences that induce the same dualistic structure. The aim of this work is to define a canonical divergence. I mean, a divergence that we can call canonical in some sense. Our reference is the divergence introduced by Amari and Nagaoka on dually flat manifolds. A dually flat manifold is a particular kind of statistical manifold that has, it has to be torsion-free and curvature-free. This divergence is given in terms of the Legendre transform between the dual affine coordinates. And this is the natural solution of the inverse problem on dually flat manifold. So the goal of this work is to define a canonical divergence that induces a given dualistic structure on a smooth manifold. The requirement for a function to be called as a canonical are the following. It has to recover the dualistic structure. It has to be 1/2 the Riemannian distance in the case where the two dual connections coincide, and they are this is the case when we recover the Riemannian geometry. So if we want to look for a canonical divergence, it has to be in the Riemannian case, it has to be 1/2 the square of the Riemannian distance, and in dually flat case, it has to be the Bregman divergence introduced by Amari and Nagaoka. So this is our target. Along this line, one proposal for the definition of a canonical divergence was put forward by Nihat and Amari. The motivation of this of the definition of this divergence function is the following. Let us start with a very simple example. Consider a real vector space endowed with the Euclidean metric and the corresponding Levi-Civita connection. In this case, we have that the distance, 1/2 the square distance between two vectors, is a potential function of this vector that we call here the difference vector. So the idea was to generalize this vector for a general statistical manifold. And this generalization is given in terms of the inverse of the exponential family. So this is the case, the real vector space, where we have the Euclidean metric and the Levi-Civita connection. This is the vector, the difference vector between Q and P. For a general statistical manifold, we have to consider the nabla geodesic from Q to P and get the nabla velocity at Q. This vector here is the inverse of the exponential function.
So, just a question: is that is the shortest geodesic between P and Q? So it takes the
the requirement would be that for Q and P are small. Are very close to each other in a way that we have only one geodesic connecting Q and P.
So it's only local?
Yes, this is a local statement, yes. And the divergence introduced by I and Amari is then defined, consider a nabla geodesic from Q to P and attach to each point of this geodesic that vector, that generalization of the difference vector, given in terms of the inverse of the exponential map. This integral is the definition of the divergence introduced by I and Amari in 2015, I guess, yes, 2015. We can call this divergence as a canonical one because it satisfies all those requirements that I mentioned before. A nice expression of this canonical divergence is given in this way, where you change the nabla geodesic. Instead of going from Q to P, you go from P to Q. Then you get this nice expression that is really useful in the application. Now we have this canonical divergence. Why we have the necessity to introduce a new canonical divergence? As I mentioned before, the idea of that canonical divergence would be to have the divergence as a potential function of a difference vector, a generalization of a difference vector. But that is not the case. At least in general, that is not the case. So in this work, we present a new canonical divergence by trying to tie this divergence to the intrinsic geometry of a statistical manifold. Let us recall that the Gauss lemma in Riemannian geometry gives us the claim that the potential, the geodesic, the Levi-Civita geodesic, are integral curves of the Riemannian distance. So this is our reference. We want to extend this result to the framework of statistical manifold in order to get a definition of a canonical divergence that is strictly connected to the intrinsic geometry of a statistical manifold. Let us start with the well-known Gauss lemma. What does it say? If you consider P and a very small epsilon as the ray of a geodesic sphere, the Gauss lemma claims that all the geodesic passing through P intersect orthogonally the velocity intersect orthogonally the geodesic sphere. The consequence of this of this well-known result is that if you define the Riemannian distance in this way, the gradient of the square of the Riemannian distance is 2 times the geodesic velocity at the geodesic velocity. The extension to a Riemannian manifold of this celebrated work given by Gauss relies on the definition of 2 new vectors. This can be considered as a modification of the difference vector introduced by Ai and Amari. Let us see with the help of this figure how we construct these 2 vectors, pi and pi star. For p and q sufficiently close to each other, consider the nabla geodesic connecting p and q. Then we take the nabla velocity at p and move with the nabla parallel transport along the nabla star geodesic up to q. This is the definition of the vector pi. If you reverse the reasoning, you get the vector pi star. So you consider first the nabla star geodesic from p to q. You take the nabla star velocity vector at p, and you move according to nabla star parallel transport along the nabla geodesic up to q, and you get the definition of p star. The generalization of the Gauss lemma is claimed in this by this theorem. If you consider this hypersurface where we modified a bit the norm, so for each vector, for each tangent vector, you get the nabla exponential map of x, and you go back via the nabla star exponential map. If epsilon is sufficiently small, you get that pi plus pi star is orthogonal to this hypersurface here. The consequence of this result is stated by this theorem. If you define, this is another modification of the square of the Riemannian distance. For p and q sufficiently close to each other, you define this function that we have called pseudo-square distance, and you get that the gradient of this function is given by the sum of pi and pi star. So this is the generalization of the Riemannian result that follows from the Gauss lemma to the setting of information geometry. So we aim to consider these 2 vectors, pi and pi star, in order to define this new canonical divergence. Let us first see if this theory is consistent with the Riemannian case. The Riemannian case is obtained from a statistical manifold when we equal the two connections nabla and nabla star. In this case, we have that the statistical manifold is a Riemannian manifold, and the nabla geodesics are equal to the nabla star geodesic. So the vector pi is nothing but that the Levi-Civita velocity vector. And the same happens for the pi star. So if we replace this expression into the equation into the relation that we get from the previous theorem, we have that the gradient of that pseudo square distance, that is pi plus pi star, is 2 times the Levi-Civita velocity vector. That is the gradient of the square Riemannian distance. Now these 2 functions coincide. So this proves that our theory is consistent with the classical Riemannian theory. Now, why this function R is important in the context of information geometry? with reference to the dually flat case, the Amari-Nagaoka divergence satisfies these nice properties. If you take the canonical divergence on dually flat manifold and you add the dual of this divergence, you get exactly that function. Very remarkably, this function here is symmetric with respect to its argument, in this case, in the dually flat case. And this yields these nice properties. This means that if you change Q with P, if you reverse these two arguments, you get the dual divergence. Other properties of this canonical divergence by I and Amari are the generalization of the Pythagorean theorem and the geodesic property. So we aim to have also these properties in this generalization of a canonical divergence. But we will see that we encounter some geometric obstruction that we cannot have this kind of nice properties. Now let us address the definition of the new canonical divergence. Consider any curve from Q to P. We can attach to each point of this curve the vector field pi TP. It is defined in this way. You consider the nabla geodesic from P to gamma of t. You take the velocity of this nabla geodesic at P and you move via a nabla parallel transport along the nabla star geodesic connecting P to gamma of t. The same happens for pi star. So the definition of the new canonical divergence, before giving that, let us first discuss this potential property that comes out from that important generalization of the Gauss lemma to the statistical manifold. This sum is independent of the path gamma connecting P and Q. Now our aim is to define this term as the canonical divergence and this other term as the dual canonical divergence. The goal would be to have that the gradient of the new canonical divergence is pi and the gradient of the dual of this canonical divergence is pi star. This is a natural requirement because in the self-dual case from the Gauss lemma we have that the Levi-Civita velocity vector is 1/2 the gradient of the square of the Riemannian distance. And in the dually flat case, we have that the nabla geodesic, the nabla velocity is the gradient of the Bregman type divergence, and the nabla star velocity geodesic is the gradient of the dual of the Bregman divergence. Unfortunately, so this is the definition of the canonical divergence. Just we take the nabla geodesic connecting P and Q, and we integrate the vector field pi t along this curve. This is the definition of the canonical divergence, and this is the definition of the dual of the canonical divergence. We take the nabla star geodesic connecting P and Q, and we integrate the vector pi star along this nabla star geodesic. Unfortunately, it's not always true that the gradient of D is pi and the gradient of the star is pi star. The best that we obtained is this relation. We have a decomposition of pi, an orthogonal decomposition of pi in terms of the gradient of x and a vector that is orthogonal to the nabla geodesic velocity vector. And pi star is decomposed orthogonally in terms of the gradient of the star and a vector that is orthogonal to the nabla star nabla star geodesic velocity. Now, this canonical divergence holds all that requirements that make divergence as a canonical. And in addition, we also have these properties that connects the divergence with its dual function. The best that we obtained is that if you change Q and P, you get that this function is a function of the dual divergence. At this point, we can discuss the comparison between the new canon. Yes.
So the f and f star functions are inverse functions of each other?
Sorry?
F and f star, small f and small f star.
I mean, this is a function that satisfies these properties here. The thing is that if you take the Taylor expansion, this function dqp coincide with d star pq up to the third order of derivatives. But if you apply the theory given by Eguchi, you can get this new relation.
But so for you want both to hold, right? So if you want both to hold, then f star and f have to be related.
Sorry, say again, I didn't get it.
So you want both left and right to hold. You want both of these to hold. So f star would have to be, I guess, f inverse.
No, they are different.
Because you can exchange PQ position.
No, they are different functions.
No, he's asking whether f star is an inverse of f.
Yes, I get it. But
It has to be inverse, right? It has to be inverse.
It's not.
It's not?
He doesn't know. He doesn't.
Oh, okay, it's not.
but maybe we can discuss later.
It has to be.
So in order to figure out the comparison between our divergence and the one introduced by Ai and Amari, we have to compare this new vector pi t and the difference vector introduced by Ai and Amari. So let us consider this curve that starts from P and go back to P passing through sigma of t. Of course, since the curvature is not zero, the two vectors are different. So recall how it is defined this pi t. You take this vector and you move along sigma star of t. The difference vector is defined by taking this vector and moving it along the nabla geodesic sigma t. So these two vectors are different. And this is the relation that connects them. This is the new vector, this is the old one. And they depends on the curvature. So if we plug this expression in the definition of the canonical divergence, we get this relation. This is the Ai and Amari divergence, and this is the new term. So if we are in the self-dual case, where this vector coincide, then because of the skewness of the Riemannian curvature tensor, we get that this term is 0. The same happens in the dually flat case. In this case, the Riemannian curvature tensor is 0. Then in both this case, this term cancels out. And we get that the new divergence coincides with the one of Ai and Amari. Just to mention a factor example where we apply this new canonical divergence. It is on a statistical manifold that we call here symmetric because we have that the nabla R is 0, and we add this more requirement on the Riemannian curvature tensor. Also in this case, the two divergences coincide. But why it's important this example? Because thanks to this example, we succeeded to conjecture that if we require the symmetry of the manifold plus that the sectional curvature, the curvature of the plane generated by the nabla and nabla star geodesic is 0. So we get that this function is symmetric in its argument. We get that this term is 0, and we obtained a straightforward generalization of the Amari and Nagaoka canonical divergence. In particular, we get this nice symmetry property. But this is just this is a conjecture. We are working on it, and we are very close to finalize also this result. As an application of this theory, we did it in the just for a dually flat case, and we get the well-known divergence, the alpha divergence in both setting classical and quantum. As an example of this new theory, forthcoming works will be to evaluate the new divergence, the new canonical divergence on the simplex of probability distribution in the classical setting and on the space of pure quantum states. So just to sum up, we introduced a new canonical divergence by an investigation of the geodesic geometry of a general statistical manifold. We proved that this new divergence is a canonical one in a way that it recovers a given dualistic structure. It is 1/2 the square distance, the Riemannian square distance, and it is the Bregman divergence on dually flat manifolds. Then we discussed some potential properties of the new divergence, and we conjectured about an intrinsic obstruction for a canonical divergence to hold in general those nice properties of the Amari-Nagaoka divergence function. That's all. Thank you for your attention.
So as we already running a little bit behind schedule, maybe there's one short question. Okay, I guess I have several, so we can discuss.
Okay,
later.
thank you.
So let's thank the speaker again.